Kinetic molecular theory is kind of a big deal when we're dealing with gases, and it is a model, it's a theory, that explains the behavior of gases. It includes the definition of ideal gases, and it takes into account the fact that the gas particles are in constant motion, and when they move, they are in straight lines. It looks at kinetic energy, which is the energy of motion of a particle, and it allows us to explain why the kinetic energy of gas particles is proportional to the temperature that we measure for those gas particles. The equation for kinetic energy is 1/2 the mass of the particles times their velocity squared, so m is mass, v is velocity in this case, it's a lowercase v. And I can look at the kinetic energy of one particle, then it's just 1/2 mv squared, or I can look at the kinetic energy of a whole bunch of gas particles, and then I'm going to take it times the number of gas particles I have, n being Avogadro's number. So if I want to find the average kinetic energy of a mole of gas, then I'm going to take kinetic energy of the mass of a molecule times its velocity times Avogadro's number. So since kinetic energy depends on both the mass and the velocity, if the size changes, the kinetic energy will change. If the speed changes, the kinetic energy will change. And it turns out that kinetic energy is not only proportional to temperature, but there's an exact equation. And the exact equation that relates kinetic energy to temperature is kinetic energy is equal to 3/2 times the gas constant R times T. So in the kinetic energy equation, the velocity is actually the average velocity for all the gas molecules. When we're looking at the average kinetic energy, the equation in red, that V is the average velocity for all the gas molecules. Some are going to be going faster, some are going to be going slower, so they'll have different individual kinetic energies, but we're looking at the collective kinetic energy of the whole thing. Okay, what this graph shows roughly on the vertical axis is the percentage of particles that have a particular energy. Horizontal axis is speed, which is comparable to the energy that the particles have. Each color represents a different temperature. So the black temperature, we have a cooler, lower temperature than the other two. We have a narrow range of speeds that our particles have, and the percent of those particles that have kind of the mid-range speed is fairly high. So I have a high percentage of particles with the average velocity right here. Where's the temperature? That's my blue line. My range increases. So I have a wider option of speeds because I have a bigger temperature range over which they can exist, and the percentage of particles that have kind of the average speed is lower because more of them have low speeds, more of them have high speeds. My third temperature, the highest temperature, range is broader yet. So I have all kinds of different speeds that my particles can have, really slow or really fast. And even fewer of them now have the average speed because, again, the range is so broad. So what we see is as the temperature increases, the percentage of particles that have the average kinetic energy decreases, but the range of those kinetic energies is much larger. Graham's law, yet another gas law. Graham's law looks at how fast a gas moves from point A to point B. And it takes into account the fact that gases have kinetic energy, so they're moving, and kinetic energy depends both on their speed and on their mass. So when we're talking about Graham's law, we're talking about two concepts. We're talking about effusion, which is the rate of a gas passing through a tiny hole, and we're also talking about diffusion. Diffusion is simply the rate of a gas moving from an area where it's in large concentration to an area where it's in low concentration. Effusion is simply a subset of diffusion. Diffusion is simply proportional to the speed of the molecule, because if it's going faster, it can cover a larger distance in the same amount of time. So as the temperature goes up, speed goes up, diffusion happens faster. If I have a high mass particle, it's going to travel more slowly at a given temperature than a low mass particle. So we have to look into both things, and so if we know diffusion speeds, we can compare two different gases and their diffusion or effusion rates. And we're going to do that by looking at kinetic energy equation. So if I have two gases, gas 1 and gas 2, and they're at constant temperature, then their kinetic energies are the same. So if I rewrite the equation, what I can get it to show me is a relationship between the speed of gas 1 compared to the speed of gas 2. So the first thing I'm going to do is remove the 1/2 because both of them have it, and now I want to end up with mass on one side of my equal sign and velocity on the other side of my equal sign. What I end up with then in the middle is the ratio of their velocities is equal to the inverse of the square roots of their mass. And that is the rate of gas 1 compared to the rate of gas 2. So if I know masses, I can figure out the ratio at which they will diffuse compared to each other. Since velocity is simply distance over time, then the ratio of distance gas A travels compared to the distance gas B travels is equal to the velocity of gas A over gas B, which is again equal to the mass of gas B square root over the mass of gas A square root. So square roots are inversely proportional to the distance or velocity ratios. An example of that is looking at the diffusion of ammonia gas and hydrogen chloride gas in a sealed tube.
In this diffusion experiment, we're looking at the diffusion of HCl gas and ammonia gas. We have concentrated solutions of HCl and ammonia on a cotton in a tube. The HCl and the ammonia escape from the solution. The gas travels down the tube. The rate at which the gas travels down the tube is dependent upon the molar mass of the gases. When the gases come together, they react to form solid ammonium chloride, which forms a white solid in the tube. We see that the white solid is closer to the HCl side than the ammonia side. This is because the ammonia has a lower molar mass and diffuses faster than the HCl.
We started talking about ideal gases when we started this chapter, and we're going to finish up by looking at real gases. The reason we need to look at real gases is because we have to remember that gas particles do have volume. They are not point masses. And at high pressure, this becomes more important. The other thing that we have to consider is when we're looking at gases at low temperatures, the particles slow down, and so they are going to end up closer to each other for longer periods of time, and so the attractive forces now become important as well. So when we're considering both of these things, and so if we work with gases when they are under conditions of high pressure and low temperature, we have to look at how both the volume of the gas and the attractive forces of the gas affect the volume of the gas. It turns out that the observed volume of a gas is less than the calculated volume of a gas because we have to consider the volume of the actual gas molecules, and we have to consider their attractive forces, which may pull them closer to each other and cause them to occupy less space than they might otherwise do. So the actual volume of a gas is equal to the container volume of the gas minus a correction constant. N stands for the number of moles. B is a correction volume factor that chemists before us have figured out for our use, thank heavens. There's a chart of these values in chapter 5 near the back of the chapter. And so the actual volume of the gas is the volume that's available to the gas molecules to move around. So we're subtracting out the volume of those gas molecules to give us the actual volume of the gas. The attractive forces of the gas also depend on the number of moles of gas molecules that we have. The more moles, the more attractive forces we have to worry about. And this affects the pressure. So again, chemists before us have come up with the correction factor for pressure, and that depends on the number of moles of gas. It depends on the volume of the gas. That's what V is for. And A is a correction factor that is related to polarity, or the dipole moment of the gas molecules. So now if we use these two correction terms, the A times N over V quantity squared and the V container minus NB, what we'll get is the real gas equation. So the pressure plus its correction factor times the volume minus its correction factor equals nRT. And the real gas equation is also called the van der Waals gas equation, and you should be able to, given the constants, figure out a pressure or a temperature or a volume using this equation. Constants for A and for B are in your book, and as it says, they're on page 224. We won't spend a whole lot of time working with the van der Waals or real gas equation, but you need to be aware of what it is and what the variables and the constants and correction factors do. And that takes us through Chapter 5, Gas Laws.